Suppose you have a bulb which requires 100 volt to power up. And let's say if somewhere far away from your city there's a power station which generates exactly that, 100 volts. Then we might think, let's just connect them with cables and we'll get what we want, right? But that's not what we do in real life. Instead, at the power station, we use a transformer and step up that voltage, let's say by 10 times to make it 1000 volt. And then, near our house, we use another transformer to step that voltage back down to whatever we need. How does this make any sense? Why do we do that? Well, transmission line wires, which are so many kilometers long, have considerable resistances which you cannot neglect. And you might know that current flowing through a resistance heats up, causing power loss. But wait a second, how does using transformers help in reducing the power loss? That's exactly what we'll explore in this video. I want to actually show you what happens to the currents when the voltage gets stepped up or stepped down. And once we get that, we'll come back over here towards the end of the video and answer our question. So, since the current everywhere finally depends upon the bulb that we're attaching over here, let's start by analyzing the current in this circuit. Before we look at the currents, a quick recap. What decides the voltages? We've seen in a previous video that the voltage over here and here purely depends upon the number of turns. So in this example, we are assuming the turns over here is 10 times less than the number of turns over here. And as a result, the voltage over here will be 10 times less than the voltage over here. So this is a step-down transformer. Now if that is not clear or you need a refresher on that, feel free to go back and check our video on Introduction to Transformers. Anyways, now let's think about the currents. For example, if you look at this circuit, how much current do you think will flow over here? Well, that completely depends upon the resistance of the bulb, right? I know the voltage, so I need the resistance. To keep things simple, let's say the resistance over here was 100 ohms. Then from Ohm's law, the current would be 100 divided by 100. That's going to be 1 ampere. So there'll be a 1 amp current flowing. It's an alternating current flowing over here. But now the question that I want to ask you is, how much current do you think will flow here? Now that's an interesting question, because this is a different circuit altogether. How do we figure that out? Well, we can use one of the basic principles of physics, energy conservation. We can say that, look, in a transformer, there is energy, electrical energy being transferred from here to here. So whatever energy is lost by the charges in this circuit must be exactly gained by the charges in this circuit. If this is an ideal transformer where there is no energy loss. And that's a big if, because in reality, there will always be energy losses. For example, you might recall, due to the fluctuating current, there will be a fluctuating magnetic field in that ferromagnet. And turns out, the fluctuating magnetic field generates heat in the ferromagnet. We call this the hysteresis loss. I'm not going to talk about hysteresis. What matters is there is heat generated. That's an energy loss. On top of that, this fluctuating magnetic field also generates what we call eddy currents on the surface of the ferromagnet, which further heats up the transformer, more energy loss. And not to mention, we assumed all the flux generated over here links over here, which is not true. Turns out in general, there will be some flux leakage, meaning more energy loss. So you get the point. No transformer is 100% efficient, but let's forget about all of that. Not for your exams, but as of now, forget about all of that, and let's assume that this is a 100% efficient, perfect transformer. Then energy is conserved. My question to you is, can you pause the video and think a little bit about, by using energy conservation, electrical energy, can you figure out how much current would be flowing in this circuit? Pause and give this a try. Okay. Hopefully you've tried. Because we are having an continuous energy transfer, it might make more sense to talk about energy transferred per second, which is power. And so we can now say, whatever is the power input is exactly equal to the power output. So power input should exactly equal the power output. And how do we calculate electric power? We calculate that as the product of voltage and current. So the input power would be the input voltage. I'm just going to write VI, that's our 1000, multiplied by the input current, which I need to calculate. And that equals the output power. I'm just going to write as V out, which is our 100, multiplied by the output current. Now, instead of substituting, let's do this logically. It's saying that the product of the voltage and the current must be the same on both sides. Now, because the voltage here is 10 times more than the voltage over here, this means that the current over here must be 10 times less than the current over here. Only then the product will be the same, right? Therefore, the current over here, don't worry too much about the direction. The current direction will have the same direction, same sense as this circuit, but don't worry about the direction, okay? The current will be 10 times less, so it's going to be 0.1 ampere. Now I want to spend a couple of minutes over here because this has confused me a lot. The equation is telling us for transformers that when you step down a voltage, the current increases. And similarly, if you were to step up a voltage, the current would decrease. And I'm like, how does that make any sense? Why is it that if the voltage is higher, the current should be smaller? I mean, from the equation it makes sense, but why? Shouldn't it be the other way around? Shouldn't more voltage give me more current? Ohm's law? Well, we need to be careful. Ohm's law works for a circuit, within a circuit. So over here, if the voltage increases, current will increase. Voltage decreases, current will decrease. But here we are comparing voltages and the currents of two different circuits. They can have whatever values they want. So don't compare voltages and currents of two different circuits and think about Ohm's law. Okay, but still, this equation did not make much intuitive, logical sense to me. And I struggled with this for years. But I think finally I have a decent explanation to understand why in a transformer, if you have more voltage, you'll end up with less current. So for this, let's go back to the basics and ask ourselves, what's the meaning of a voltage? Well, remember, voltage basically means joules per coulomb. And so 1000 volts basically means 1000 joules per coulomb. What does that mean? That means that if there was a coulomb of charge that moved from here to here, then it would lose 1000 joules of energy to transfer that to the blue circuit. So let's say here's the coulomb of charge and this cloud represents 1000 joules. When it moves down, it would lose that 1000 joules to the blue circuit. Okay, and on the other side, we have 100 volts potential difference here. What that means is 100, let me write that over here, 100 joules per coulomb. And since here we are gaining energy, this means that if a coulomb were to move from here to here, it would gain 100 joules of energy. Again, here's our coulomb, and as it's moving, it will gain only 100 joules of energy. And so now the question is, how can this coulomb lose 1000 joules, but this coulomb only gains 100 joules? How can that be? Here's how I like to think about it. This coulomb talks to this coulomb and says, hey, because you're giving me a lot of energy and I can't take all of that in one go, maybe I'll take multiple rounds. Maybe I'll just take 10 rounds, and in each round I will take only 100 joules. And that's what it does. And that's why the coulomb over here has to travel 10 times faster than the coulomb over here. Now, of course, the animation is not perfect. First of all, I'm not showing 10 rounds. I'm only showing 5 rounds. And the current is supposed to be alternating. I'm not showing any of that just to keep things simple. But you get the idea, right? Because we are stepping down voltage, we are forcing this coulomb to accept less energy. And as a result, it has to go faster and take multiple rounds. And that's why stepping down voltage increases the current. And of course, something similar is happening near the power station side as well. Because we are stepping up the voltage, this time it's the coulomb that is receiving the energy that is traveling slower because it is receiving way more energy than the coulomb over here can give. And so stepping up the voltage has to decrease the current. So now we can look at the big picture. Without the transformers, the transmission lines would have had 1 amperes of current. But with the transformer, by stepping up the voltage by 10 times, we have reduced the current in the power lines by 10 times. And so now if we factor in the resistance of these transmission lines, which is very real, then remember the power dissipated, the amount of heat dissipated per second in the transmission lines is given by I square R. And since the current over here is 10 times smaller than the current over here, the power dissipated over here would be 100 times smaller than the power that would get dissipated over here. Which kind of makes sense, because the charges are flowing very slowly over here, less collisions are happening, and so you would expect low power dissipation. Now at this point I had one more confusion. Yeah, I used to be a confused kid. See, people always say power loss or heat dissipated is I square R losses, but hey, power can also be written as V squared by R. And so if I look at this equation, with more voltage I would get more power loss. So doesn't that mean stepping up the voltage actually increases the power loss? What's going on over here? Can you pause the video one more time to see if you can explain this yourself? Alright. Remember where this comes from. This comes from Ohm's law by substituting V is equal to IR. And Ohm's law is always applied across a resistor. So this voltage is not this voltage or this voltage. This is the voltage that would come across the resistor. And that voltage is basically I times R, which means over here, since the current is 10 times smaller, even that voltage across this resistor has also reduced by 10 compared to the voltage over here. And so, yeah, because there is some voltage drop happening, not all the 1000 volts will appear over here. Some of the voltage drop will appear over here. But that amount is much smaller than what you would get here. A lot of that 100 volt would get appeared over here. Does that make sense? So even voltage wise, if you look at it, power dissipated has reduced. Stepping up voltage helps in efficient power transfer. And now you may ask, well, then why just step it up to 1000 volt? Why not say 10,000 volt? And you're right. In reality, the transmission lines carry currents at very high voltages, hundreds of thousands, or sometimes you step it up to even millions of volts. And finally, you may be one of those people who might say, why million when we can do a billion? I mean, if you step it up to 1 billion volt, then the current would be almost negligible. You have almost perfect power transmission, right? Well, yeah, theoretically, yeah, but remember, to step up voltage, you have to put more windings appropriately, so good luck with that. But even if you do that, well, there are other problems. Now with 1 billion voltage potential difference, we can ionize the air, and that will start giving us lightning everywhere. That's not good. So yeah, there are practical limitations to how high you can go. But if you keep that in mind, then yeah, higher you go, better would be the power transmission.